Hi there, and welcome to the first video in a three-part series covering linear regression. The majority of the material of these slides comes from Christopher Bishop's book, but I recommend reading Kevin Murphy's book if you want to dive deeper into the material. Now, I know that neural networks and deep neural networks are all the rage in the news right now, but linear regression and the linear classifiers that we'll talk about in another lecture series are the real workhorses of machine learning in industry. Why? Well, it turns out that you can get a hell of a lot of insight into correlation and class separation with these methods. In addition, they're easy to understand and are usually on the lower end of the computational resource requirement spectrum. I worked on IBM's Watson system for insurance and for healthcare, and I can tell you from experience that you can do a lot of really interesting and non-trivial work with these algorithms. Now, you can't have a decent lecture about math without knowing what the symbols stand for. I've tried to keep my notation as close to that as used in Bishop's book, but there are some small differences. For example, a capital denotes a vector, or an uppercase denotes a vector, and an uppercase that is bold denotes a matrix. The function y of the vector x are the predicted values of our inputs of the vector x. Z are the targets associated with each input vector x. And z sub I is the target value of the ith example. W sub 0 is a bias term, but please don't confuse this with bias in general. Phi is a basis function. Function E is an error function, but E with a tilde over the top is the regularized error function. The calligraphic letter D represents our training data, which is composed of sets of vectors x and targets z. And Phi with the dagger represents the Moore-Penrose pseudo-inverse of Phi. Everything else that you find should be consistent with the usage in Christopher Bishop's book. So imagine we have a nice sinusoidal function, like we see here in green. We sample points from this function, and the points that are sampled happen to be a little noisy. So here down below, we see that the variables associated with what I just described. So we have the generating function here, sinusoidal, but it's got a little bit of error, and that generates our data point z. And we're trying to create an approximating distribution y of x that, with the same amount of error, would give us the sinusoidal. So let's assume we don't know the function that generated our data points, and we'd like to approximate one that describes our points. What do? Well, the first approach we might take is to try to fit a line to our data points. So we want to find a function y that takes our input data x and gives us a value as close to z as possible. Since we want to do this for the data points that we have to sum up the error that we get between y and z for every data point, and then we want to minimize it. I think this process should be familiar to most of you. Starting at a very basic level, let's assume that our function y is the most basic form of a polynomial that we can create. That is, it's described by only one parameter, w sub 0. That means that we have the associated total error value given by the error function e. As you can clearly see, this form of the line doesn't fit the data very well. Not only that, the parameters of y don't use any of the information of x. So let's try a higher level polynomial. Now we have a function of y that has two parameters. One of the parameters is affected by x. Again, we can clearly see that although this version of y fits the data better, it still is not very accurate. What if we use a higher level polynomial? Here you can see that the level 3 polynomial version of function y fits the data quite well. You should also notice that the error function for the last 3 versions of y hasn't changed. The only part of the error function that changes is the function y. Let me repeat that. This part of the error function hasn't changed over the last 3 examples. It's only been the function y that's changed to incorporate each new higher level polynomial that we've been introducing. So if a level 1 polynomial is better than a level 0, and a level 3 polynomial is better than a level 1 polynomial, then a polynomial greater than 3 should also be better, right? Well, the answer is yes and no. The error is undoubtedly better because with a high enough polynomial, it will go to 0. However, as we can see in the graph, y does a terrible job at approximating the true distribution. This is because with a high enough polynomial, that is, a polynomial that has an order greater than the number of points, it's trivial to find a function that directly goes through every single data point. This is a very basic example that shows how algorithms in machine learning can be very powerful if you know how to use them and you understand what they are doing. Having a low error is not always a good metric just by itself. Now that we have an intuition for the problems that we're dealing with, let's formally define things. As mentioned before, we have inputs vectors that are labeled as x, and they are associated with an output value z. You might have noticed in the early slides with polynomials, the function of y had a similar form throughout the polynomial progression. There we go. Here is the general form of that function. You'll notice that the phi function, that is the basis function, wait a minute. Basis function? Well, yes, a basis function is just a function that allows us to transform the inputs x to a different space. Why would we want to do that? Well, sometimes we can transform the input data to a space that makes the problem of regressing or even classifying the data easier. The functions in this new space can even be nonlinear. Wait a minute. I thought we were doing linear regression. Well, if you look at equation number 4, you'll see that it is linear with respect to the input variables x. That means it is linear in terms of w. Putting this all together, we see a familiar form of the sum of least squares error function, utilizing this new form for w. There are tons of different types of basis functions. Basis functions are closely related to a concept called kernels that I'll be covering in a separate set of lectures. You should recognize this first basis function for polynomials. It's what we used in the examples in the first part of the lecture. As I said, there is lots of other possibilities for basis functions. Usually, each choice of basis function also brings limitations to the model that we have to understand. For example, the polynomial basis function is a global function of the input variable. That means any change in one area of the function affects all other areas. Regarding notation, I would like to mention that the basis function can also be written as just the identity function. You might find some notation in these slides or future slides where you see W transpose X instead of W transpose phi of X. Just remember that they're equivalent and interchangeable in this framework. The Gaussian is a very important basis function that's used quite often in things like Gaussian processes, which we'll discuss in later lectures. The logistic sigmoid function is very useful in a type of classification called logistic regression, which we'll cover in a later set of lectures as well. So far, we've talked a lot about what one should do when trying to solve the problem of finding the best fit line for the data. We've talked about minimizing the sum of squares, but we haven't talked about how to do that. We do this by setting the gradient of the error to 0 and minimizing according to the unknown parameters. In this version of the error function, if we rewrite the sum over vectors of phi as the design matrix, we get this form here, which is it's just a fancy name for saying that we're creating a matrix out of the individual vectors of phi that pertain to each input vector. So in other words, this is just a matrix of vectors that represent the input vectors x in the new space created by the basis function phi. Solving for the gradient by setting the error equal to 0 and solving for w, we see that the optimal value for w can be achieved using the normal equations of the ordinary least squares problem. You may not recognize it, but equation 8 here, with a little bit of reordering, can be seen clearly as the normal function. If that still doesn't look familiar to you, I can just rewrite it in this form, which you should recognize. Now, the steps between equation 7 and equation 8 are not trivial, but if you're interested, using equation 71 and 81 of the Matrix Cookbook can help you derive those steps. So, this shows us that the optimal W is equal to the pseudo-inverse of the design matrix multiplied by the target values of Z. Here, this pseudo-matrix is actually the Moore-Penrose pseudo-matrix, which just means that when the matrix is square and positive semi-definite, the Moore-Penrose pseudo-inverse is actually equal to the inverse of the matrix. Okay, well that seemed pretty straightforward. We have the normal equations, and we can solve those to give us our optimal value of W. So why do you think computing the solution using the normal equations is not such a great idea? Well, if the design matrix is not full rank, the inverse of phi squared doesn't exist. How can this happen? Well, if you remember back to your linear algebra days, you might remember that you can't uniquely determine a solution for n parameters with less than n data points. Furthermore, none of the n data points that you have can be linear combinations of the other data points in your set. This is one scenario where replication of data points is bad. Even though replicated data points in a large data set can help defeat noise, this is not helpful in the smaller data sets. This can also occur when the values are very large and there is very little variation in the numbers. This is why it's sometimes important to center and normalize data. Even if it's full rank, you're not guaranteed anything because it can still be ill-conditioned. Both of these are examples of where things, when done with pure mathematics, happen to work out and work out nicely, but when done on a computer, they fail horribly. This is something to always keep in mind. We're not working on systems that have infinite precision. As we noticed in the polynomial example, when we went up to the 9th order, we were severely overfitting our function onto the training points. So what can we do to combat that? Well, one very common option is to split our data into training and test sets. We fit our function to the training set, but we evaluate it using the test set. The root mean square error allows one to normalize for differences in the size of the training and the test sets. As you can see in the graph in the lower right, we have a plot that represents the information from our polynomial example that we had earlier. As you can see, choosing a polynomial with order between 3 and 8, they all perform roughly the same. It isn't until we get to the 9th order that we see the extreme overfitting occur. Okay, well, we have that information now. What else can we do about it? One option is to get lots and lots and lots of data. If somebody asks you, how much data do you need? The answer is, how much data can you get? And then they say a number, and then you say, yeah, get more than that. Having a lot of data doesn't guarantee that you won't overfit, but it helps quite a bit with the overfitting problem. As an example, look at the two graphs at the bottom. The one on the left is a 9th order polynomial basis function representation with 15 data points. To the right is the same equation, but trained on 100 data points. Notice how much smoother the one on the right is? It turns out that overfitting is a problem that is a general property of maximum likelihood. So far, we've been focusing on the least squares method of finding the model parameters. And as you'll discover in the next lecture, least squares represents a specific case of maximum likelihood. Another technique that can be used to combat overfitting is called regularization. Regularization is the addition of constraints to an equation. If you're familiar with Lagrange multipliers, you will already understand how this works. Essentially, we're forcing the equation to minimize not only the original equation, but additional equations. In the example shown here, we have a scalar times the L2 norm of the weights. This forces the weights to stay small and not blow up. In the 9th order polynomial example, we saw that the polynomial expression line made sharp turns in order to fit the training data completely. These large turns are caused by large values. So forcing the weights to be small, we're forcing the polynomials to be more smooth. In this specific example of L2 or Euclidean regularization on sum of least squares, the scalar term is affected by the variable lambda. As you can see, by changing the value of lambda, we can change the strictness of the fit. This, however, doesn't solve our problem of determining parameters for best fit, because now we've exchanged the problem of figuring out the number of basis functions to model with having to figure out the best lambda to model. You're not limited to using the second norm as your regularizer. The L2 norm is just a commonly used regularizer, and when used with sum of least squares, it has a special name, ridge regression. You might have heard of the Lasso method. Well, that corresponds to just having a Q value of 1 instead of 2. As I mentioned before, finding the correct lambda can be difficult. Skipping the details, the expectation of the squared loss can be broken down into 3 parts: the bias squared, the variance, and the noise. If our goal is to minimize the expected loss, then we need to find the optimal balance of bias squared and variance. The image on the right shows how the squared bias, variance, bias squared plus variance, and test error all relate to one another in an example problem different than our polynomial problem. What I want you to see and to internalize is that decreasing the variance or increasing bias by themselves doesn't guarantee you good test error. The minimum value for variance plus squared bias in this image is when lambda is at a negative 0.31, which is close to the value that gives the minimum error on the test set, but it's not. Remember, minimizing the variance and squared bias does not guarantee the minimum error, but most of the time it will get you very close. I may have lost a few of you on that last slide, so let me reiterate what bias and variance do. If we look at the picture that looks like a set of 4 archery targets, we can get an intuitive feeling for bias and variance. Here we have high variance and low bias, high variance and high bias and low variance, and low bias and low variance. Obviously, we would hope to have low variance and low bias, but usually we're not so lucky with our data sets. The 2 function depictions at the bottom of the slide are to help you get a more intuitive feeling for what this actually means in a linear regression setting. In the picture on the left, we have 2 training sets depicted by black X's and red circles, as well as a blue dotted line that shows us what the original generating function was. Bias refers to how far the mean of the 2 training sets is off the original generating function. Looking at the picture to the right, we see that variance is the distance that the training data functions vary over the blue generating line. If it still doesn't make sense, pause the video and think through each of these images. Well, I hope you're not asleep and have learned something in this lecture that covered basic linear regression. Up next, we'll be covering Bayesian linear regression. Thanks for watching, and have a great day.